Introduction to systems of coplanar forces. When a force is resolved into two components exactly along the x and y axis, that is called rectangular components. These components in here, f of x along the x axis and f of y along the y axis, they both are rectangular components. Since they are rectangular components, they making a right angle triangle, upper and lower one. And these rectangular components can be expressed into scalar or Cartesian forms. The scalar notation for it, the force in the x direction equal to F cos theta, and the force in the y direction equal to F sine theta. But why? We know that right angle triangle, we know cos, if we apply here the rules of trig, cos theta equal to adjacent over hypotenuse, which is f of x on the x direction divided by f. When you solve for f of x from here, f of x should equal f cos theta. And the same thing applies for the component on the y direction. So if we say sine theta, but this time for this angle in here, pay attention to that. Sine theta for the upper triangle equal f of y over sine, sorry, f of y over f. And that when we solve for f of y equal f sine theta. And that's how we express the components into scalar notations, either it's the x component or the y components. We should pay attention to this special case. When we have similar triangles, you can see that triangles ABC, the smaller triangle, is similar triangle to the big one, to this upper or lower triangle. That's why we call them similar triangles. For this special case, if you take the x component, which is f of x corresponding to the a side, and the f of y component is corresponding to the b side. That's why here when we say f of x, the x component divided by the hypotenuse or divided by the f of the force, f of x over f should equal to the corresponding sides in there, which is a over c. And we do the same things here when we solve for the f of x equal to, just solve for it, f times a over c. Same thing for the y component. The y component, f of y over f, the force itself, take the corresponding side, f of y corresponding to it, it's b, divided by the f is corresponding to it, which of course it is c, and solve for f of y. Paying attention to the negative sign in here because the f of y, it's in the negative direction. Cartesian vector form or the Cartesian vector notation. We take the components of the force. We have got the force F. We take the components on the x directions and the components on the y directions, and we multiply them by a unit vector. The unit vector here, it's I, which is equal to 1. When we multiply anything by 1, remains as it is. So on the x directions, we denote it by I. And then we do the same thing in here. We take the f of y, we multiply it by the unit vector j, which again, the magnitude of it is equal to only 1. But also, we remember that they have only these unit vector, they got only magnitudes and they are dimensionless. So these magnitudes in here can be expressed in this form. The force F equal to the force in the x direction multiplied by the I component, which is the unit vector component, plus the force in the y direction component multiplied by the j unit vector. And if we have a third dimension or we have third axis, which is going to be z, for example, that we have to add f of on the z axis, of course multiplied by the k unit vector. However, in this case, of course, we're dealing only with two-dimension problem, so we keep it as it is. Now, the resultant force of the coplanar forces, when a few forces acting on a point, they all acting on the same point, we are going to resolve these forces, all of them in here, into rectangular components, each one of them. So each force is going to result in one component on the x direction and the other on the y direction. Just pay attention to the negative sides of the axis. Now, F1, when we resolve it into two components, into x and y axis, is going to be, of course, F1 on the x directions I plus F1 on the y direction j. We will do the same thing for F2, but paying attention again to the sign. F2 is on the negative x axis now. On the same thing for the F3, you're paying again the attention to this negative sign, because it's on the negative y sign. Therefore, the resultant vector should look like the Fr, which is the resultant force, equal to F1 plus F2 plus F3. But how are we going to add them? We are going to add all of them, just put them back here. We take the same thing in here, we put them in this form, then we are going to collect like terms, all of the i's together and all of the j's later on together, etc. So to summarize, when a few forces or when many forces acting on the same point, we are going to sum all of these forces together to get the resultant force. But each force first has got two components on the x and y axis. So we have to resolve each force first on the x and y axis, then sum all of the forces on the x-axis to get you the resultant force on the x-axis. Sum of the forces on the y-axis to get the resultant force on the y-axis. And if we have a z-axis, again sum all of the forces on the z-axis to get the resultant force on the z-axis, and then apply the Pythagorean theorem to get the final resultant force. Add all of them, take the square root, of course, of adding all of them together. For the direction angle, we are going to apply tan theta. Tan theta, we apply the adjacent over hypotenuse, which is the y resultant force on the x resultant force. And of course, theta itself is equal to the inverse of tan to the absolute value of the resultant force in the y direction over the resultant force in the x direction. Even if it's a negative, we are going to ignore it. See you guys in the next video for practical problems or questions to solve.